okay. So why is this nitrogen? So label each of these peaks. What is this peak?
That's 1s2.
1s2. Let me right? Okay. This is 1s2 because we're talking closest to the nucleus, highest strength of attraction, meaning highest binding energy. 2s2, and we can see the same intensity size. So we know it's the number of electrons. This is 2p. So how do you know it's 3?
0.5.
Right, so this is the first level of the electron. Second intensity represents the second electron. So you can see up another distance of the same intensity is 2p3. So that has, what, 7 electrons? So it's nitrogen. Good. Next. Don't know. It's right after the notes. 26. Page 26, thank you. Next one, would you guys put? A. So the answer is A. Beryllium has a greater effective nuclear charge than lithium and more electrons in the 2s orbital. So comparing these, what is this peak representing here and here?
Number of electrons.
Okay, well, that you can see there are 2 electrons here, right? And there's 1 electron here because of the difference in intensity. But what else? What is that electron, or what is it representing? Was in the question. Which sublevel? Right, this is the 2s2 sublevel. This is the 2s1, and that's the intensity difference. But then why is there a difference from here and here? Why is the energy, binding energy different? Yeah, Han. That's not the actual reason. You're right to say the lithium has a, actually no, lithium's 1 valence electron. Add to that in terms of the trend. They both have nuclear penetration, though, because these are both 2s orbitals. S orbitals have nuclear penetration. Who has more nuclear penetration? You can see it here, right? Beryllium, okay, because we have a 11 binding energy versus like a 5. But why? Zeph, thank you. It's simply because it has an additional proton. It's more about the nuclear charge than the nuclear penetration or the electrons. So talk about Zeph on that one. And it says it here, greater nuclear charge. Okay. Next one, is this 3? Yeah. What's your answer for 3? A, okay, so we did have a lot going on in these graphs. Good. Sulfur has greater effective nuclear charge than phosphorus. What does that basically mean? How many protons does sulfur have? Proton, sulfur, look at your periodic table. 16 protons versus phosphorus.
Miss Emma.
Yes.
Pardon the interruption. Would you send Jeff Taylor to the office and he'll be back to you?
Can you come in a couple minutes? Thank you.
Will you guys be okay, sir?
You just tell me why is okay, so sulfur's got 16 protons, phosphorus has, with me, 15 protons. So we have a difference in Zeph, so that's one of the first things you should notice. Label these for me across. What is this? 1s2. 2s2. 2p6. You should see the difference in energy intensity. 3s2. 3p4. You can see it doubles in intensity. You should be able to read these very quickly now, okay? There's no question about what each of these are representing. And then the top one, what's the only difference here? 3p3. Right, so that intensity is slightly different, so that's 3p3 there. And then you can see the energy is slightly, so 1.06 versus 1.00. Why, again, is this one higher? Whole stability thing. So this one has 3 orbitals in the 3p, electron, 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 and then a doubled electron, right? What is that causing? Right, electron repulsion is really the reason that this one has a lower amount of energy, to binding energy, because it has the repulsion factor plays into it more than the distance from the nucleus, for example. This one has 3 electrons in 3 separate orbitals. So this one actually has a higher amount of attraction, binding energy, versus this one. Okay, so that's our big difference there. 4, what is this, 4A? What do you guys get? A, okay. This one I'm not going to go over in depth because you can see the difference here. This one versus this one. This is still talking about the 3s electron. You can still see that the intensity here. What's the intensity difference? Is this 4B? Oh, the question for 4B. Okay. First of all, the difference is this one has how many protons? 19 protons, and sodium has 11 protons. So that's the difference in the binding energy. This one has a higher binding energy because of the higher Z. Okay, and then 4B.
Good question.
Huh? Where's my? We had a question. We didn't have answers, but but I talked about this. Is this the one that says, looking at the following, would you explain the difference in intensity for the 3s?
The signal intensity.
Signal intensity? Yeah. It's C. Sodium has 1 valence electron, but so does potassium.
But it's an S3S. There's 2.
Oh, thank you. I was wondering, I didn't make, only 1 electron in the 3s orbital for sodium. Do you see that it's 3s, which is the period before, so the 4s1, but this is 3s2. This is only 3s1 because of the period difference there. Actually, I'm going to make myself make sense. So that was question 5 for me, 4B for you guys. Yes? Okay. This is question 6 for, no, 5. Is this 5?
Yeah.
What, is it this one? No? Which one am I?
No, that's not 5 for us.
This one? This is 5 for you. Okay. This is 5 for you guys. Given the photoelectron spectrum, which of the following explains the relative positioning of the peaks on the horizontal axis? So these questions ask you to look a lot at the graph, but really you're trying to figure out which is the most true, which one doesn't contradict itself in the middle of the answer. Okay, so which is the best one here? D. Titanium has a greater nuclear charge, but the 2p sublevel experiences greater shielding than the 1s sublevel. The shielding is just because of the energy levels rate. You can see that this is on the graph it indicates Ti2p, which is the 2p sublevel. It's comparing the 1s sublevel of oxygen and then carbon. So really what you're looking at is Zeph, so the protons, meaning the binding energy, and then merely that the answer didn't contradict itself, because some of the other ones contradicted themselves or weren't reasons for this particular question. Sorry, I keep moving the thing forward. Okay, so like, for example, oxygen has more valence electrons than titanium or carbon, so more energy is required to remove them. Is that a correlation? Not at all. Like, that has nothing to do with the question, nor is that actually a true statement. Oxygen has more electron-electron repulsion in the 2p sublevel than Ti, so than titanium and carbon. That really doesn't have a whole lot to do with the binding energy. Binding energy is related to Zeph. Okay, the last part, titanium atoms are present in greater quantity. Who cares? Like, that has nothing to do with this either. This has nothing to do with mass at all. Okay, so think about that as you're going down too. Okay, last one for you guys. Yeah? This one. Given the photoelectron PS of scandium, above which is the column best explains why scandium only makes a 3+ than a 2+. What did you guys say?
C.
Good. C. Why?
There's the values over there are very low, so it's very easy to remove that third 1s, or not 1s.
So what is the 0.77 regarding?
0.77 is the 3B.
And then the 0.63? Right, so this is like 4s2. You can see the intensity different just barely, but it's there. It's 2 electrons there. And this is actually the 3D1, which is where we end at SC on the periodic table. And those values are very close, but like the off-ball principle, we always talk about 4s2 and then 3d10, because technically the third energy level is technically a little higher, but you can see that for this particular case, it actually is so close it's almost indistinguishable, that there is a difference in those sublevels. Okay, you're feeling good about PES? Graphical analysis, you have to draw one of these on your free response. Okay, draw one and answer one like from a multiple choice standpoint. Okay, let's talk this stuff we've been doing. This is where we left off yesterday. I'm going to get through as many Lewis dot diagrams as possible. So put your atomic structure stuff away, pull back out your bonding stuff. And then do you guys remember playing with these? Okay, we have a lab on this tomorrow. Now, Honors Chem had you do kind of the basic level things. We're going to get into more of the more complex ones, specifically the bond angles. Okay, bond angles and more about the structure of the atoms and why they are the way they are. So here we go. Let's jump in. This is what we did not get to yesterday. Draw yourself an example of a Lewis dot structure in terms of the most simplest form. You can draw them with bonding electrons in the middle as two dots, or you can draw them as a dash. You will see me draw them as dash most often. But a couple lights off. We're going to get sleepy. Some of these pictures are hard to see.
Lord Jesus, Lord.
Well, I will. Okay, can you see okay? Oh, Josh, go to the office and see Mr. Lowry. Jump in, okay? Okay. So this is something you've seen before. The terminology behind it, you read some on your SMI thing. So the ones that are between them are called bonding electrons. The ones that are on the outside are called either non-bonding electrons, or what's another name? Lone pair. Okay? And so those are just terminology pieces that you want to be familiar with. And we did talk, I believe we said yesterday, the duet rule, right? Did I tell you about the duet rule versus, okay. So the octet rule is that most things will meet octet, and I hate that we even call it the octet rule because there are so many flippant exceptions to that rule. There are very few things that will attain octet. They're mostly anything in the second period on the nonmetal side, but like beryllium, it's good with, let's see here, this one's good with 6 valence electrons in its bonding area. This one's good with 4 valence electrons. Hydrogen's good with 2 valence electrons in its bonding area. Those are the exceptions. And then there are things that are expanded octet that can reach 10, 12, 14, 16 valence electrons. So octet is actually probably a rare occurrence for us in AP. Moving on. Yes, yes? Give me some indication. Thank you. Okay, so we talked yesterday as well about the double and triple bonds and how the bond distances and the strengths differ. So the correlations that you should make are, let's say, decreased, let me go with this. Increased bond order, and bond order is another term that we use to describe double bonds, single bonds. So usually we call it a single bond of 1 bond order, a double bond, a 2 bond order, and a triple bond, a 3 bond order. We're really going to jump into bond order when we get to the molecular orbital theory, which is actually new theory in the last 2 decades. Previous chemistry teachers I worked with have no idea what the molecular orbital theory is because they didn't learn it in school. I was fortunate that they had discovered or come up with that theory, so I knew what it was. So increasing the bond order usually decreases the length of the internuclear distance, but what does it do to the strength? Increases it, okay? So we have these direct and indirect relationships that we need to be aware of. And then, so 2 really good options that you are going to be more familiar with are oxygen is a double bond and nitrogen diatomic is a triple bond. So the double bond has an internuclear area with 4 valence electrons, and the triple bond has an internuclear area with 6 valence electrons. Okay, this is an example of bond polarity. What my people who did one of the trends, which is probably the most important trend that we're talking about here, if we're talking about bond polarity. Electronegativity, okay? So the difference in electronegativity values is really the only way you're going to be able to predict a bond, a covalent bond, because we're all the way covalent now. Yesterday we talked about ionic pretty briefly. We'll talk about ionic again in our next unit. We're pretty much done about ionic for the drawing of them. You still know their properties because you guys did that nice activity yesterday in our picture. So covalent bonds have to share electrons. Sometimes they don't share equally. So if they're not sharing equally, we've got an area. So if this is my bond, 2 electrons are in it. If they're spread out equally between my 2 sides, that's called a nonpolar bond or a nonpolar covalent bond. Why is it nonpolar? Anybody? Well, I can call them whatever. I can call them X and Y. That's not the part actually that I'm concerned about right now. What do you see that's true about my electrons? Hey, he's either sitting in the back of the room or he's in the copy room. Yeah, there. So do you see? Yeah, so that electron is equally spaced away from X than it is the other one is from Y. Basically equal sharing. Okay, if you have equal sharing, neither side is more positive or more negative. And so the only way that's going to happen is if you have relatively similar electronegativity values. That's the only way. So give me two things that might have similar, not the same, but similar EM values. Look in the periodic table. So I know like oxygen, oxygen, wood, chlorine, chlorine, any diatomic will, because they were exactly the same. Who's similar? Let's think covalent too. So you're thinking non-metals, right? Nitrogen, oxygen. They're right smack dab next to each other. They might be pretty similar in their EN values, so probably very non-polar. Oxygen and fluorine maybe. Oxygen, sulfur. Nitrogen, phosphorus. Carbon and oxygen. No, actually they're more polar because that's one away. Carbon and nitrogen. Anything that's relatively close. Now you're gonna have to make guesstimates. Do you remember in honors game you got the sheet with the electronegativity values on it?
Yes.
You're not getting that. You don't get it. Heck, honor doesn't even, they don't even get it on their final exam. They get it on their test because they need to learn it. But you know the top number is what? 4, and that's where? Fluorine. So the values increase up. 4.0 is fluorine. Everything else is less than that.
So it's just, we're supposed
You
to.
just know the general.
So if
Trend.
we had to guess, you're saying if they're right next to each other, it's probably close, but you said like carbon and oxygen, one away, it's probably polar.
I'll show you the difference in values in just a second because they're very
Okay.
close.
What about stuff that's in the same group, like not period? Will that be
Being
the
like
same, like right next to each other, like oxygen and sulfur, but not oxygen and
selenium. Yeah. So if they're touching each other, I'd say they probably. There are always exceptions. I'd say they are non-polar. Okay, so the unequal sharing, meaning let's say X and Y, two different elements, of course, in their shared location, X has the electrons held closer to it. What would you say about X versus Y? X is more electronegative, so electronegativity value may be a 3. This Y might have an electronegativity value of maybe a 1. So the difference is a 2 value, and I'll show you the difference here in a second. But this is definitely a polar bond, and the way that we actually describe the polarity of it, we don't draw these stupid little electrons here. We draw an arrow above it. Do you remember drawing these? Like this. You're pointing the arrow towards the negative value. It's partial negative, by the way. It's partial negative. There's this little partially negative area here. This side is partially positive. It's like the lowercase sigma. And then you draw the hash mark on the partially positive side. Okay.
When we did this in honors, wasn't it just like we were supposed to do it towards?
The more electronegative one.
Okay, so I think I just remembering it by the
Because
positive
this is
one
on the
gets
positive side. Yeah, the hash looks like a positive, so that's why we draw on the positive side. But this indicates it's called a dipole moment. And so it creates a dipole moment, and that's what we call that arrow, the dipole moment. So if I say draw a dipole moment, I mean draw an arrow. Okay, so this is an electron cloud model, nonpolar covalent, equal cloud space, polar covalent, partially negative, partially positive. Please get used to seeing and drawing those partially positives and negatives. That's going to be very common for AP. We didn't do as much in honors. Ionic, why no connection of the cloud? Right, there's this cation got smaller because it donated electron, portion makes the anion get bigger. There is literally no bond. So why do we call it ionic bond? I have no idea. Bond does not mean touch, does not mean to like hold hands. Bond does not mean really anything for us. Bond, this is more of an ionic attraction if you really want to get serious with it. So the values, I'm going to go forward. The values based on this are, where do I have this? Oh, it's right here. Okay. So right smack in front of my face. A very small difference means it's like actually 0.46. It's going to be nonpolar. If it's between that and usually like 1.7-ish, but usually a pretty significant value is going to be polar. But if it's a very large value difference, it's going to be ionic. But probably more than anything that's going to help you remember it's ionic is if it's a metal and a non-metal combination. That's going to be, from left to right on the periodic table, very big difference in electronegativity values. and then obviously a very big difference, possibly to the point where it actually donates the electron versus sharing it. So those are some actually values that you saw back in honors. So for the example up here, hydrogen versus chlorine, chlorine's a 3.0, hydrogen's a 2.1. Those are not values you need to memorize. Okay, you're going to get used to seeing these though. That difference is 0.9, so then what would you classify its bond as? Right, polar because it's between the 0.5 and 0.7. So it's polar covalent, and then what would you draw here? Pointing, right, the dipole moment pointing towards chlorine, hash on the positive side, which is the partially positive side. Okay, what do I have here? So these distinct differences in electronegativity that I have indicated here, they're more of a continuum. They are not exactly, there is no hard, fast rule. Like if it's at 0.5, it is nonpolar. That's why it's called a continuum, because some of these values are published in different books as different indicators if it's going to be polar covalent or nonpolar covalent. So usually between-ish 0 and 0.4-ish is going to be our nonpolar realm. And then as you get closer to like the 1.6, 1.7, your ionic realm. That stuff in the middle, though, it's kind of like, it depends. There's exceptions. So don't just try to memorize those numbers. Just think about like the nature of the bond whenever you're putting two things together. But one other note, this is usually my highlighted stuff's probably the more important things right now, is that whenever you're looking at the trends on the periodic table, looking at the electronegativity values, the larger the difference means that they are very attracted to each other, because as you create one side more positive and the other side more negative, that's when you get into electrostatic attractions where you get opposites attracting. So they actually create usually a stronger bond. Sometimes then when you get too large, so too large of a difference, it actually is going to become ionic. And guess what? Isn't that the strongest type of bond? So it's going to get to the point where even it's so different, it actually does ionize, and those electrostatic attractions come into play because of the opposites attracting, meaning it has more ionic character. So ionic character versus covalent character. Ionic character just means you have a large charge difference. Can I move on? Vicious? Okay. Lewis dot structures. This is your process. Can I do an example with you to show you the process versus you write down the entire process?
Yes.
Yes? Two things to note. I have this in red. Do not be smarty pants and go straight to drawing. Count those dang valence electrons first. Because if you don't, you're going to end up with the wrong number of valence electrons at the very end. Count them first. It takes you about 3 seconds. After that, you're going to try to do a symmetrical drawing, choosing a central atom, and then putting different ligands. Ligands are our legs, our atoms on the side. So after we make the ligands, we're going to start adding our valence electrons. Giving everybody octet, except for hydrogen
and boron and beryllium.
Right, so the small things. And then if we have extras, we smack them on the central atom, because the central atom probably can handle it. Okay, so let me start with an easy one. I'll come back to this, I promise. This is a good, good picture shot here. Okay. So let's start with what's the name of that?
Carbon tetrafluoride.
Carbon tetrafluoride. Good. That was fast.
Count the
Thank you. Well, you probably need periodic table if you don't have one out yet. Okay, count valence electrons. Ready when you are. How many does carbon have? 4. And you knew that because that's the group it's in. Fluorine has 7. So 4 times 7 is. So that's 32 total. Total valence electrons is 32. You should write down this example. Okay, write down all these examples with me. And who got to the end of the NSMI? Big and bold. What does it say?
count them.
Draw the Lewis.
It said draw the dang Lewis structures. Even if you think you're smart enough, like, I totally remember that. You probably won't, okay? Just draw it. It does not take that much time. 32 valence electrons. Who's the center?
Carbon.
Carbon. You usually choose the least electronegative because it's like, all right, sure, I'll share with you and you and you and you. Who's going to share with? Obviously the fluorines, right? We got 4 fluorines, make it as symmetrical as possible. What are these dashes representing? So 2 electrons, right? A single covalent bond. In this case, do you think that single covalent bond is polar or nonpolar? Why? Great. We got carbon over here, which is like a 2.5 or something, and then fluorine's a 4.0. Yeah, it's like really cool. Okay, that's just something back in your mind for a second. 2, 2, 2, 2. So what do I need to do? So give everybody octet. So the first step was count valence electrons. Second step, choose a central. Third step, ligand it up. Ligand is this word here. Okay, those are like legs atoms added to it, and then octet. So that's 8 there, 8 there, 8 there, 8 there. Okay, so then when you count them up, you go 8, 16, 24, 32. So then you're like, all right, nice, got mine there, okay? That's your process of drawing. I've started with an easy one. Does anybody remember the shape of this, the molecular geometry? Tetrahedral, good. So, I will. Diamond, you see this. It's not in my class. Hola. What's up? I do. Can you give me just like a couple minutes? Thank you. Okay, just give me like 3 minutes. You guys can hang out. That's fine. Yeah. Okay. So dipole modes to go out. I forgot to send those to Mrs. Milam. Okay, they all go out. Okay, so what we have here is a part or a molecule. If you think of it as a big circle, we have an equal electronegativity kind of difference outward, upward. Sorry, that's a negative. Outward and outward. So we have an equal distribution of this partial negative charge, right? Would you consider this molecule polar or nonpolar? Nonpolar. Okay. Nonpolar molecule, but polar covalent bonds. So you can have a nonpolar molecule with polar covalent bonds. Nonpolar molecule describes how the geometry and the polarity of the bonds interplay together. And I'm going to go over that in more depth in a second. But the polarity differences of the bonds are just because of the electronegativity values of the elements. 2 different concepts, but they play well together. Okay. So I want you guys to take on drawing ammonia, formaldehyde, carbon dioxide, and sulfur sulfate. Go ahead and do that right now with somebody while I get them what they need.
I can ask it after.
Thank you. Give me a second. So ammonia. I'll talk about the geometries in a second. Okay. Ammonia, formaldehyde, carbon dioxide, and sulfate. If I print them for you, is that best? Okay. Okay, I'm going to start with ammonia, simply because I think have we all accomplished that one? Ammonia?
Yeah.
Okay, how many valence electrons? 8. With me? Please be quiet for a second. 8 valence electrons, who's your center? Nitrogen, and then bond, bond, bond. Hydrogen's met its max, that duet. Where do the last electrons go? Right, this is a lone pair. Now, special fact about lone pair. Lone pair have 2 very, very negative electrons, right? They do not like to be even close to bonding electrons because these are electrons here, and these are electrons, right? So these have pushing power. They repel bonding electrons. They repel to the point where instead of being a flat T, it repels the bonds down. What shape is that? Triangle pyramid.
Yeah.
This is the shape. So if it were flat, it would be like that, really flat 2D. But you can see it's 3D, just a little bit, because this imaginary lone pair up here is pushing down, and it's making it have a 3D appearance. Not very much, but I can bend it. It's a 3D shape. So that's called trigonal. Why would it be called trigonal, people? But why is it called trig? 3 legs, tri means 3. Okay. Trigonal pyramidal. Because it looks like a pyramid. Thank you. Pyramidal is pyramid. So formaldehyde, how many valence electrons? 12, I believe you. Okay. Central is usually carbon. Carbon likes to bond 4 times, so it is very cool at being in the middle. So then where does the rest of it go? Let's make it symmetrical. Okay, so 2 hydrogens, 1 bond each. I'm going to put them on left and right to make it symmetrical. Right, so if you put oxygen up here by itself, carbon does not have enough bonds. You could put a lone pair in carbon, but it's very abnormal. It does not tend to have lone pairs, because if it does have 5 electrons around it, I'm not going to lone pair. If I put a lone pair here, technically carbon looks like it has 2, 4, 6, 8. You're right. But in terms of formal charge, which you're going to get into, you read about it last night, the formal charge of it is based on the number of assigned to it. And that's half of every bonding pair and all of its lone pair. Okay? So that's 1, 2 for its lone pair, 3, 4, 5 because I'm taking half of the bonding pairs. 5 valence electrons around carbon is not normal. It's usually, if you look at the valence number from its group, it has 4. So that's why actually I know up front that's not a valid Lewis structure. So I'm actually going to double bond it with oxygen. That looks bad, but it's a double bond. And then you'll see I've already used up 8 electrons, so then where the rest of them go? Right, because oxygen so far only has 4 assigned to it, so it needs 2 lone pair to get it up to octet. So then this shape, because there are no lone pairs on the central atom, does not make a 3D shape. So what is the shape? What's the shape? So this was trigonal pyramidal.
Trigonal planar.
Right, trigonal planar. Because of the flat appearance to it. Okay? This is making some sense. The terms will be coming to play more tomorrow. Yeah.
Okay. Why on that one specifically did you do the? It got half of the.
Oh, let me explain formal charge in a minute. I just wanted to expose you up front. I'm going to do a whole slide on it.
I had a different question. If, like, obviously hydrogen we know is always, it wants 2 valence electrons. But if we're doing some of the other exceptions that you said, like beryllium and boron, do we have to know those?
It'll be based on its formal charge.
Okay.
It's like a secondary way to confirm something or deny something. So carbon dioxide is our next option. How many valence electrons? 16 valence electrons. Okay. I think you all probably put carbon in the middle, oxygen on left and right. Okay, symmetrical as possible. It does double bond. So because basically what happens is if you have 16 valence electrons and you put everybody for octet, you would have had 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. You're like, oh no, I've got too many electrons. 4 too many. So what you do is you condense them into 2 double bonds so that they share, taking away the 4 additional that you had. So I'm taking away 2 from the oxygens on the outside and making them double bond, right? But what do you notice I still have here? Right, because I actually need to take away all the lone pairs that I'm trying to force into a shared relationship, and that would create my 16. 2, 4, 6, 8, 10, 12, 14, 16. What shape is that?
Linear.
Right, because you'll notice there are no lone pair. So no lone pair cause usually the shape to maintain its 2D shape, which is a linear shape. Because like how else do you connect 2 dots? Through a line. That's it. Okay? So you tell me oxygen and carbon, polar or nonpolar covalent bonds? Right, carbon and oxygen, nitrogen's in the middle of them, right? So then you'll draw a dipole this way towards oxygen, a dipole this way towards oxygen. Okay, so 2 polar covalent bonds. But look at the molecule as a whole. Left and right, what are the partial charges? Negative on this side, negative on this side. Is there a difference in the distribution of the electrons? No. So then what would you say? It is a nonpolar molecule. Nonpolar molecule. Despite the fact it has polar covalent bonds, the geometry allows for the polarities to cancel, causing the nonpolar molecule to form overall. I'm dipping into this now because this is one of the hardest things for people to usually understand. Can I do the last one? Sulfate? Okay, sulfate. So how many valence electrons do we have? And did you account for the charge? Including the charge? So sulfur has 6 plus 4 times 6 for oxygen plus 2 electrons because of the net charge of 2. So that's 32 electrons. So who goes in the middle? Sulfur. And then 4 oxygens on the outside, right? Where did you guys add all your oxygens? I mean your electrons. All of them in the oxygens. Well, okay, I'm here, and sulfur has 8 electrons around it. The 2 negative charge comes into play, but not because of that. So if you put octet on everybody here, you are good. Huh? Right. So the way it looks right now, it looks correct, right? It looks like it's got 32 electrons. Now here's where we have to confirm. This is formal charge. I'm explaining to you through an example, and then I'll have this slide for you. Formal charge is how do you confirm if a Lewis structure is valid or invalid? Because there's another way to draw this one. It's through expanded octet. I'll draw it here. It's exactly the same structure, except I've relocated 2 electrons, right, from the lone pair position to a double bond position. Why is sulfur able to take on more electrons than octet? You read this in your reading lesson. Anybody? Yeah. Okay, expanded octet. Ready? I'm like writing this for you today, okay? Expanded octet can only occur with anything that's in the third energy level with access to d orbitals. What I mean by that is that you know 3D exists, right? There's my little clicker thing. So I'm going to point this directly over here. You know that this whole, okay, so that's 3s2 from sodium and magnesium all the way over to argon is 3p3 or 3p6, right? Well, these 3p's actually have access, and extra pockets to access this 3d orbital if they have enough electrons. Well, obviously when they're in the 3p position, they just don't have enough electrons. But they're still in the third orbital, right? If you're still in the third orbital, the third energy level, you still have access to 3d orbitals to stuff extra electrons. And that's what I mean by expanded octet. Normally, they max out at 8. But if you're phosphorus, sulfur, chlorine, or argon, so write those down. Phosphorus, sulfur, chlorine, or argon. Those very commonly will expand octet. Not always, but if you got to make it happen, you can make it happen, people. Those 4 plus anything below them can access d orbitals. So if you can access d orbitals, guess what? You can expand your octet. Okay, who's definitely never going to expand octet? Who does not have access to d block?
Argon.
Argon is actually, despite the fact it's a noble gas, it can bond. So who's never going to do it? Anything above it, so like what?
Carbon.
Carbon,
nitrogen,
nitrogen, oxygen, chlorine,
neon.
neon will bond, it's too small.
Hydrogen.
Hydrogen, yeah, well,
Beryllium.
obviously, those will not either. Okay, so this is the shorthand version of expanded octet. Okay, let me tell you more. I've not even touched formal charge yet. Formal charge, the way you calculate it is you take the number of valence electrons assigned to it in the Lewis structure. Number of valence electrons assigned to it in the Lewis structure. Subtract number of valence electrons, I'm going to say like on the PTOE, so like number of valence electrons it actually counts. Okay, so let me show you how this works. How many valence electrons are assigned to sulfur in the Lewis structure? The way the assignment works is if it's a lone pair, it's all yours. But if you're bonding, you only have to, you're assigned half of them. So in this double bond, how many are assigned to sulfur? 2, because it's like there's 4 total here, half of them are assigned to sulfur. So 2, 1. So that's 3 so far? 5. So it's 5. So it's like 1, 2, 3, 4, 5, 6. So sulfur is assigned 6 in this model here. Sulfur 6, right? How many does sulfur have assigned to it on the PTOE? 6. So 6 minus 6 is 0. Okay, so the formal charge of sulfur is 0 here. Okay, let's do that for this oxygen up here. Assignment, these are lone pairs, it's all it's, right? So that's 6 so far, plus this one, 7. So do you see I'm taking half the bonding ones, right guys? Yeah. So formal charge of oxygen up here is 7, which is assigned to it in the model, minus how many it should have? 6. I may have just flipped that. It's, I always, if it has an extra electron, it's the number that's assigned to it minus the assignment. I try to give you guys a formula for it. You can just see if it has too many electrons or too few. So oxygen should have 6 electrons, right? Yeah. It has 7. So it's got extra electrons. So what do you think its charge is, its formal charge? -1. Sorry, I flipped that for me. I was doing it from memory. I tend not to actually think about the formula because if you look at it and you look at that guy, you can see it has an extra electron. So formal charge is 6 minus 7, which is -1. Okay, so oxygen has a -1 formal charge. It's not its actual charge. It's a formal charge assigned to it from a Lewis dot model. So then guess what this one has, guys? Also -1. Around it because it's a model. It's an identical system. So -1 formal charge. Formal charges are not real charges. Okay, then what about this oxygen? Right. Tell me why. 1, 2, 3, 4. Okay, so 6 around it. How many should it have? 6. So there's no difference. So the formal charge is 0. Same deal here. 1, 2, 3, 4, 5, 6. Should have 6. It has 6. Formal charge of 0. Guess how sulfate gets its -2 charge?
Wow, those 2 -1.
Because of the formal charge. So basically, the formal charge should agree. The net formal charge should agree with the charge of the polyatomic. Okay? This whole Lewis dot structure equates to a -2 charge, which is what sulfate has. Why is this one not true then? What do we have here? Formal charge.
-1.
-1. What does this one have? -1. This one? -1.
Like
-1. Okay. Sulfur. Right. Y plus 2.
has
How many assigned to it?
4 assigned.
4 assigned to it. How many should it have? 6. So it's lacking 2 electrons, right? If you're lacking 2 electrons, you take on a more positive charge of 2, right? Plus 2. So, despite the fact that this one nets to what? -2. This one is more favorable because formal charges of 0 are more stable than formal charges of anything else. Okay? Lewis dot structures, you can write them and draw them however you want. This is the less valid one. This is the valid one. So this one is wrong and this one is right. Okay, so formal charge, what are the couple rules that make them stable?
0.
0 is preferred. What else? Net should be
Equal the total
charge.
of the ion/molecule.
Okay, and I think that's pretty much it. Oh, there's also one more, like, if you have, so right, I'm gonna let you guys read and write down some of this, and then I'll tell you some more. This is the process we just went through. I think it's beneficial for you to write something down for yourself about formal charge. So formal charge of 0, very favorable.
Can we go back to back in a
To the
second, up
steps.
to the first one where, I don't know why sulfur was 2+.
Yes, so I'll go back in a second, yep. So don't you need to. You good? So 0 preferred, net to equal polyatomic ion charge, and 3 opposite charges near to each other is more preferable as well, because if you have, for example, in that previous model with the sulfate, -1 fraction on north, south, east, and west, right? We had -1, -1, -1, -1. That's a lot of -1s actually kind of close to each other, and they tend to repel negatives and negatives, right? So it's better if you do have 2 charges next to each other that they're opposite in charge, because they actually help stabilize the molecule because of the nature of opposites attract, make things more stable. So that's kind of the third rule. Opposite charges are nearby if you have opposite charges at all. And you work with formal charge a little bit, and that's really just going to help you decide which is the best Lewis model. Okay, so let's go back to that sulfate example. Here, so for example, on this one, we have a bonding pair here, 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 and here, and sulfur, in this case, is assigned half of those, so that's 4 total. So 4 are assigned to it. And then sulfur on the periodic table is in the 6th group, so it has 6 valence electrons normally. So 4 assigned minus the 6, oops, it's the other way, I'll just keep doing that. 6 assigned to it, minus the, 6 valence electrons minus the 4 that are assigned to it, give you a +2 overall.
Oh.
So basically, if sulfur is supposed to have 6 negatives, and unit only has 4 negatives, it's more positive than it should be. It's more positive by a quantity of 2.
Okay, so in the blue, did you write it opposite number?
Yeah, that's what I said.
Okay.
But if you think about it that way, like it should have 6 electrons, it only has 4. It's missing 2. It's got a 2+ charge.
Okay.
You can think about it both ways, but that's opposite. Okay, can I go forward, guys? Let's do one more example like this, but you guys draw them. Oh, this is the rules. Did I miss one? More electronegative one should get the lower permanent charge. That one makes sense though too, doesn't it? Because if you're more electronegative, you should have a negative, generally a negative formal charge if you have to have an odd charge at all. Okay, so that's one additional one. All right, so tell me which of these is the best Lewis structure for carbon hypochlorite? There are 4 of them. Basically, think about how many valence electrons each of them should have and how many are assigned to them on the model.
Sulfur.
Anybody else see anything different? So tell me your logic, Kevin. Carbon likes in the middle, but tell me more.
Oxygen. Oxygen. That formal charge right there is 6. Let's see. Oxygen's actually valence electrons.
Okay, so 6 formal minus 6 assigned is 0. Okay, one more thing though. What's the net charge of this molecule? Should it be? If I say carbon hypochlorite.
No, it should be 1.
No.
No,
0, thank you.
I forgot how
Carbon.
I forgot how numbers work.
No, it's actually not carbon hypochlorite, but it's a compound. A compound that's neutral should have a 0 formal charge. Okay, so oxygen commonly will double bond. Commonly, because if it doesn't, what's its formal charge going to be? It's going to have 2 lone pairs here, another one, and then a bond, which would be, may not have a -1, right? So oxygen commonly will double bond. Halogens commonly do not double bond because they want 7 valence electrons. They have 7 valence, they should have 7 around them, meaning 6 assigned through lone, and then 1 assigned through a bond. So halogens commonly make a single bond. Carbon loves making 4 bonds and never having lone pair, because that should make it have 4. That's its form. 4 assigned, and the 4, that's its valence number, should give you a 0 formal charge. So this one gives you a 0 formal charge on every single one of them. 0 plus 0 plus 0 plus 0 is 0. So formal charge that. You should have known pretty immediately that this carbon's out, because you'll never see carbon off to the side like that. And if this chlorine's double bond, usually it's symmetrical. This one in this case would have a positive 1 formal charge because it's missing an electron. Oxygen generally does not want to be in the middle because it does not like to share. It is very electronegative. Okay, we're learning so many things, guys. Oh yeah, resonance structure. Okay, we'll review formal charge and then some more.
Yeah, I just don't know how I'm supposed to draw it. If, say, I draw it how I normally would think it would be, and the formal charge isn't low, then I would be like, oh, well, what am I supposed to do now to make it a low formal charge?
I'll go through an example.
Okay.
Because you guys will draw in one way, and I'll tell you how to draw that. So resonance, this is something that is more common in organic chemistry than in innate chem. But it is a term that most people have a misnomer for. It does not mean to flip between identical Lewis dot models or valid Lewis dot models. So I'll show you the example down here with benzene in just a second. Basically, if we come to the point where we're like, hey, I'm going to draw the Lewis structure like this, and that's my example down here of benzene. And let's say you put the double bond on the top and then the left and right versus somebody else being on the bottom and left and right. Well, they're both equally valid Lewis structures. So they're equally valid, meaning their formal charges are appropriate, their atoms are in the correct orientation, everything's equal about them. You should call them both valid, right? Because they are both valid. However, instead of actually saying these 2 or 3, however many number you can find, are equal, you say that they have resonance with each other. So you do not say that they have, 18 million valid Lewis structures, because actually they are 1, and they're a meshed version of the 2 or 3 Lewis structures that you decided upon. And that meshed version we call a superposition. I'll let you write down some of that, then I'll continue. Everything is the same. Basically, the electrons are in different locations. The atoms are in the same location. And so if you do draw multiple Lewis structures, and you would like to, display each of them to say that they have resonance, the only way that a chemist would see that you're trying to show it has resonance is if you draw the double-headed arrow in between them, like I did down here, and then usually you put a bracket between them, around them, to say these are resonance structures of each other. These are multiple valid Lewis structures. I don't know what it actually looks like. We do, though. We think we do, anyway. It's actually drawn, I'll show you this example here. So benzene, this is the lazy man's way of drawing benzene as a hexagon, right? And some people will just put the double bonds there when you equally could have done it like this one over here. So instead of putting the bonds in a single location, you put them in all locations by drawing a dashed model through it. So, ooh. Shapes. Okay, so you draw a dashed line to say the bond is here or here, but it's actually a mesh between the two. So this right here is supposed to represent the best way to draw benzene, for example. So the superposition means that instead of saying, let's say this guy, you can obviously tell in this model it's a double bond, but in this one, it's a single bond. Instead of saying it's a double or single, you say it's a 1.5 bond. Okay, so this part down here is important because it's going to relate to our strength and length. Okay, so this one, so double versus single, which is a shorter bond. Double, okay, so the double bond is shorter. So what would you compare a double bond to a 1.5 bond? Would a 1.5 be longer or shorter? Longer. Would it be weaker or stronger? Weaker. Weaker. Okay, so despite the fact that you think there's a double, single, double, single, double, single, it's a conjugated system, it's actually not. It's a 1.5, 1.5, 1.5, 1.5, 1.5. So I can have you compare that to something else. Let's say a single bonded creature. And the single bonded creature would be longer and weaker than the 1.5 bond. Okay, so the resonance structure is not an intermediate. It is an intermediate of the bond length and strength, but it's actually a specific model that doesn't look like this or this. It's a mesh. Okay, so let's look at this one. You guys draw ozone. Draw all of its resonance structures. Ozone. First one we do. Thank you. You're counting. What we don't finish today, we'll finish tomorrow. So. Are you remembering some of this though? No. Okay. Not this. Well, okay. So ozone has how many valence electrons?
18.
18 valence electrons. So you're drawing them in a straight line, at least this far, right? Then what's next? After you kind of finish your first of those dots.
Put 3 electrons on the left and right.
Three lone pairs.
Yeah, 3 lone pairs.
So that's good.
And then the opposite one did the same thing.
If you did that here, and you gave everybody octet, how many valence electrons do you have on here? 20, right? So you've got 2 too many. So you must erase 2 lone pairs and make them share. Who are you erasing? Doesn't really matter. The 2, maybe 1 here from that one, and then 1 here from the middle one, and make them share instead of saying, okay, you can have 1 and you can have 1. Does that satisfy it? Yes, I chose to erase the right and the middle one. What could you have chosen also? Left in the middle one, which would have given us this structure. Right? Equally acceptable. Basically mirror images. If they're equally acceptable, there are 2 loose dots. There's really nothing else you can do here. So then to say it's resonance, what do? Draw a double arrow and brackets. Do put brackets, okay? That'll say these are resonances of each other. So the best way to draw it actually is like this. Say it's here and here. So what's the length of this bond? 1.5 again. Bond length is 1.5 again because it's basically each of them have 1 bond and they share the second bond. So if you take a second bond and you split it in half, it's half. So 1.5 bond, 1.5 bond on each of the locations here. All right, so carbonate, go for it. The 1.5 or the resonance? You mean this part here? This part here? Okay, so you know you got your 18 valence electrons and you have your general skeleton. And then is it the part where you make the double bond? Or when I drew a second version. I just need to know where. Good? Okay. So carbonate, how many valence electrons, guys? 24, so 6 from each of the oxygens gives us 18, plus 4, plus 2. So this is 24 valence electrons. Okay, so then what is our 24 valence electrons? What are you guys drawing for your structure? Carbon's in the middle. Okay. So, and you try to separate them as equally as possible. So I'm drawing this as kind of a trigonal appearance. Why am I double bonding one of the oxygens? Carbon loves bonds. It does not like balloon. So this is us kind of learning how the tricks of the trade. So then the oxygen only needs 4 more. This oxygen needs 6 more. So we should have 8, 12, nope, 16, sorry, 24. So the double bond for that one I chose, or Kevin chose, put on top. What else could we have done?
Oh, so there's going to be 3.
3 resonance for this one, because we have 3 equally acceptable Lewis structures with the double bond in a different location, which is what I mean. The atoms stay the same, the bonding electrons change just a hair. Okay, so then the last one would be down to the other side. Okay, so each of these actually are missing one more piece. If you have an ion, and I didn't draw this on the sulfate one because I was doing it for a teaching example, you have to draw the brackets around the ion and say it has a -2 charge. Why does this have a -2 charge? Do not say this carbon has a -2 charge. Who has a formal charge that gives it this overall -2 charge? Okay, good. So this oxygen on here is a -1, -1. I forgot some lone pairs there. Sorry. This one has a -1, -1 because they have an extra electron, and then ditto, -1, -1. And so those summate to -2 charge. So, and then just for kicks and giggles, resonances we have to put our extra bracket to say these are all resonances of each other. Who's feeling this a little bit here? Like you're okay? Yeah, you're good. Okay. So let's talk about bond length again. Give me a second, Heidi. Bond length. I have an oxygen-carbon bond on each of these, right? That's a single bond. That single bond there then is going to be sharing the second, the double bond here. So it's going to share the second bond that I've added across 3 locations. So basically what you're doing is you're taking one bond and you're dividing it by 3 locations it can coexist in. So then what's that additional part that we add to the bond length? 1/3. So each of these things get an additional 0.33 as its length and strength, right? So each of these bonds are what? 1.33. Because all you're doing is taking the one that changes its location and splitting it up across all locations it can be. So it has to divide itself in 3 times. So each bond length is 1.33. Is that longer and or shorter, stronger or weaker than a 1.5? Because it's closer to 1, right? So it's longer than a 1.5 because it's closer to the 1 side than the 2 side, and it's weaker. All right, thumbs up.
Do we ever have a bond length of less than 1?
No, because it has to bond, right? Okay, so I need to go back to anything that I just did right now. What do you say I need to go back to?
Well, I wanted to practice like the
like
unknown
unknown
charges.
Okay.
Because I don't know what I would, like you drew it, so I knew what to do, the 2 differences. But
You're going to do that.
a question I had about the formal charge was like, on one of the rules it said the total of the formal charge is supposed to equal the charge on the ion.
If it is an ion, right?
So on the one that was SO42 minus, the one that we said was right had a 0 of a formal charge.
It had a -1. It had 2 oxygens with a -1 each. So 0, 0, -1, -1, and then sulfur in the middle. I did it over here, but it has a 0. So that's 1, 2, 3, 4, 5, 6. So these 2
The 2
-1s,
oxygen.
they sum to be -2, which is sulfate's charge. And that's better than this one because there's 0.
Is that
And this one's got a lot, I mean, it does some to -2, but this one has a -1, a -1, -1, -1, and a +2. These charges are too big. That's more favorable. We'll practice more. Okay, so last thing is actually isomers and then less than on Chem. We'll do 2 examples of that. So this is a question that they'd love to ask me short FRQs on the free response. Basically, they'll give you a formula, and they'll say, draw an isomer of this. So this is ethanol, right? We've got C2. What's the formula of ethanol?
C2H6O. H5OH.
Thank you. So this is better because this indicates the functional group of the alcohol. Okay, so we have an alcohol group, but we can also say the formula is like Clayton said, C2H6O. This gives us just all the atoms involved. The formulas of isomers are exactly the same. The way they are arranged is slightly different. So we can actually make an ether. Remember what ether? Something on either side of the O. There's something on either side of the O. It's like the ether money. No? Like ether money. It's just to look like whiskers. Ether. Whatever. Okay. They will expect that you can rearrange, even if you don't know what an ether is or alcohol is, because organic chemistry is technically not in our curriculum, but it is, and everybody says we should teach it, except for College Board, but then they test us on it. So we teach it. I have already complained to College Board. I'm on their review committee to say look, people, you can't test us on stuff you said on our curriculum. That's why the scores were so low the first year we initiated the new curriculum. Anyway, so you should be able to manipulate the drawing to be a different structure but the same formula. That's all an isomer is. So we got isotopes, ions, isomers. Any more I words? Okay. Yeah, there you go. So that's basically what that is about. And I'll move on. In organic chemistry, you deal with isomers a lot. You have to look at these Newman projections. You know where the bonds are oriented. It's kind of fun. Pretend you're looking down a bond. So here's a Newman projection. You look down the length of a bond, and if this is carbon with hydrogen, that's the front side of the bond, and then the other side of the bond, you have another carbon and hydrogen. That's a Newman projection. You're looking down the length of a bond. Anyway, that's next year. Okay, odd number of electrons. This is kind of the last bit, but it deals with a more application part of it. Who's ever heard of free radicals? Okay, free radicals, not so good for us, okay? They oxidize the insides of our body. What could we combat free radicals with?
Antioxidants.
Antioxidants. So oxidants are combated with antioxidants, which are foods like what? Blueberries, anything with dark pigments, right? Blackberries, strawberries, acai, maybe not apples because they don't really have dark pigments. Like anthocyanins, they don't have dark pigmentations inside. So generally, anything without a paired electron is called a free radical. If you don't have a paired electron, you desperately want another pair for your electron. So you react with anything in your regions. And so that's why they're very sometimes hazardous, because they will attack molecules to force them to give up an electron or to force them to emit an electron so they can grab it. And that's very uncontrollable. So we have free radical domino effects that can affect, for example, ozone, because it'll force an electron off of ozone, which we then lose ozone, right? And then that's bad because we have a big ozone hole. So some of the free radicals that are initiated originally come from CFCs. What are those? Fluorofluorocarbon, yes. Fluorofluorocarbon, yes, thank you, CFCs. And so they've actually eliminated the uses of CFCs in some of the nations because they want to try to keep our ozone hole small. Okay, so I'll let you read a little bit of that. But this relates to the single electron that's not bonded in a Lewis structure, not with a double lone pair in a Lewis structure, and that's what we call them odd numbers because there's not one with a pair. So I have some examples for you here. So they steal the electron. They're very disruptive to the natural cycles of usually atmospheric chemistry. This is in your cell membrane. It's a free radical chain reaction where one takes them and then it bumps to the next one and then the other one takes it. There's chlorofluorocarbons, antioxidants, erosion of cell membrane, and then here's another example. This is in ground level ozone. Well, actually, no, this could be ground level or upper level ozone, where you create a domino effect of decaying of ozone due to the free radical oxygen, free oxygen radical. So those are applications. Shake your head, smile, something.
We learned so much.
I know. We have one more. Can you draw a? I have 2 more minutes. Can you draw an incomplete? That is not complete. Meaning, not octet. Incomplete octet. For beryllium dihydride and boron trifluoride. Draw those for me, and then I'm done. I told you today, yesterday, that today would be a talky day. Thank you
I
for.
haven't been talking. It's just so many concepts that are different. Like all exceptions.
I think it will sink in when you sleep. That's usually what happens. Your brain does a lot while you sleep. It makes sense of many things throughout your day. That's its job.
Some of us don't sleep.
I was just about to say
So,
that. I was
beryllium-
I don't do a whole lot of sleeping.
So beryllium, we wrote down that one's supposed to have
An exception,
4
right?
valence electrons.
And you'll see why when you share the bond nature. Come here, Lewis. Come on up. You be my drawer. Don't let me down.
Which one?
Both of them.
You're wrong.
He's good under pressure. Under pressure. Okay, beryllium dihydrate. How many electrons total? 2 from beryllium, 1 each from hydrogen good. Beryllium or boron trifluoride. Go for it. So boron trifluoride could be called ionic. Beryllium dihydride. Beryllium and hydrogen. Despite beryllium is a metal, technically, it commonly forms covalent bonds though. There are some things that are so small, they end up sharing their electrons versus giving them up because beryllium's ionization energy is very high. Because it's got a really small atom, so the electrons are very close to its nucleus, so it doesn't really want to give up the full electron, but it's willing to share. So small things sometimes, despite you think that it's going to be ionic, might be covalent. And that's why I'm trying to be very clear that this one in this case is covalent. Boron trifluoride, how many valence electrons total? 24. He counted before.
8 times 3 though.
He counted before. So boron is okay to have 6 valence electrons. Okay? Thanks. Okay, I'm done. So sorry. You guys are going to do these 6. I'll take these off as we need to test for geometry. So page 1, I thought we'd actually get these in class, but write these down. Page 418, if you want to see a picture of this textbook or come in here for teal and do that, that's fine. Number 43, 45, 55, 65, 79, and 80.
Are these on the website?
Yes, I've already updated the website, yeah. Why do you think I gave you an odd? You can check your answers in the back of the book. You should know it about yourself.
Are any of those involving
Oral charge? Yes. That's why I do.
Yeah.
Okay. All right, announcements.
I'm gonna
Electrons.
know how to do it.
Hey,